Okay, hi guys. Now we're gonna do the E&M portion of the equation sheet. But as you know, for 2020, E&M is just E. Although, of course, there are plenty of interesting, fun questions that they can come up with, but just testing you on electricity. So let's get started. So this first equation. So I think in the last video, maybe you couldn't see so well when I was writing on here. So I'm gonna sort of go back and forth here. So this first guy, I'm gonna write like this. Okay. So remember that this can be just K. All right. And with all these big fancy absolute values, remember this is just, right, this is the magnitude, right, where you don't worry about the signs of these, you're just worried about the size of them, okay? You, of course, get the direction by your like charges repel and your unlike charges attract, right? So that gives you the vector component here. Of course, this is the magnitude of Q1, magnitude of Q2, and then R is the distance between them. So this force is really only good for the force between two charges, right? Boom, that's it. This next equation, we more commonly write, at least I usually do, we write it as that. And this is really, okay, you totally can't see that. I just realized that. And watch me move that up. Yay. It's like it never even happened. Okay. So FE equals QE. This is the way I like to write it. And this is a vector equation. This is like full on vector equation. So let's say my electric field is like this. And I put a positive charge here. That means my positive charge, right, means that my electric field and my force are in the same direction. If I put in a negative charge, then that means that my force goes the other way. And that negative here gives you an F equals negative. That, right, that tells you about the direction. It's parallel, but some might call it anti-parallel. Okay, cool. This guy is good old Gauss's law. Surface integral over a closed surface, which is our Gaussian surface. And this Q is really quick, right? That's the enclosed charge. That's the charge that's enclosed in the electric field. This quantity is also called flux. Okay? Cool. These two sort of go together. Let's look at this first one. EX is negative dV dx. So when you go on in physics, you will realize that this is really something called a gradient, which gives you the vector quality to the EX. But basically, it tells you, right, let's say I have 0 volts, 10 volts, 20 volts, 30 volts. Then what that tells you is that our electric field points toward decreasing potential. Okay, that's what that means. It's decreasing potential. And the steeper it changes, and I can't really indicate it with my arrows here, but the steeper this change, the greater the magnitude of the electric field. The next equation here is just literally this turned around, okay? This looks an awful lot I'm using a pen that barely works. I'm going to put this back down here. This looks an awful lot like that. Okay? Let's put those together. And we need to put it together with that. Okay, leave this for a second. This is the definition of the electrical potential energy. And that's Q times V. The other way to think about that is really the definition of potential is potential energy divided by Q. In the same way that the electric field was the electric force divided by Q. Okay? So with a combination of this, and this, you actually get all the same beautiful things. Maybe I'll save that for a different video because we're just trying to do an overview here. But there is an equation here, which is not on here, which the counterpart is not on here, that is useful. And E sub x, oops, can't see. E sub x negative dv dx. We also had this counterpart, and this is good for an electric potential energy and the electric force, or it's good for the gravitational potential energy, okay? Or it's just good for, I give you any old U versus X, right? And the slope anywhere, oh look, these are equilibrium points because the slopes are 0, which means the force is 0. Remember all this? Okay, so this is useful and not on your equation sheet, but it sort of is because that is. Okay? Groovy. Let's keep going. This equation, what is that good for? It is only good for the potential from a point charge. This is V is KQ over R. So this is for a point charge only. Okay? You'll notice it has, like, in the equation, it has the sum, right? So this is obviously if you're trying to figure out the potential for a set of charges, right? And remember, that's a scalar, so it's just a scalar sum. So that's nice. Cool. All right. Now we're here. Let me move this. All right. Let me fold this over so I can get this up here. All right. Ooh, what is that? All right, we just saw some V's, so we know that that's a potential. Q is some kind of charge, and C, what is C? This is for a capacitor. I'm drawing a parallel plate, but you could have any kind of capacitor. This is for a capacitor. Okay, so let me write down, that said delta V is Q over C. So for a parallel plate capacitor, if you have, a plus V and a minus V, right? Delta V here is 2V, right? So sometimes we have 0 in V, 0 negative V, whatever. But it's really important that when we say delta V here, and sometimes we just write V because we like to mess with you, okay? That this is the potential difference between the two plates of a capacitor. I'm drawing a parallel plate capacitor. You can have cylindrical capacitors, you can have spherical capacitors, okay? But a capacitor means that there's a charge plus Q and a charge minus Q. Okay? That Q is this Q. It's the magnitude of the charge on each of the plates. Okay? Cool. This C is kappa epsilon naught A over D. That is that a capacitance for anything? No, that is very specifically, that is your parallel plate capacitor, where this is your area, and that's your D. Epsilon naught is your good old epsilon naught. Kappa is the dielectric constant. So what's in here? Kappa for a vacuum is 1, right? And then if you put in a dielectric, it'll be, kappa is always greater than 1. So putting in a dielectric increases the capacitance. And remember that capacitance is purely a geometric thing here. It tells you for a given potential across it how much charge can I load onto those plates. Okay? These are your series and parallel. For capacitors, of course, your resistors are down here. You'll see that they're the opposite of each other. All right, we are doing well here. I'm going to skip this one because here's another capacitor thing. This a lot of people get confused about. U sub C is the energy stored in a capacitor. It's really stored in that electric field that's in between the two plates. But that's not a potential energy of charges, right? Like that. It's not that. It's the potential stored in the capacitor. And that's given by, 1/2 Q times delta V, which is generally the least useful version. 1/2 CV squared, or Q squared over 2C is often useful. The idea here being they like to ask questions like, if the energy, or how will the energy change if I change something? And that changing usually involves some kind of geometric change or dielectric change. And so what that means is it changes the capacitance. And whether it's connected to a battery or disconnected to a battery, certain things are constant. And so you want to use one or the other of these. Okay. Groovy. We are almost done. This is the definition of current, just sort of the rate at which charge passes you by. These are more current things that are sort of at the microscopic level that very, very rarely are tested. So we're not really going to go over those. Okay. Here, let me fold this again so you can see. All right, we're almost there. All right, resistance. So the resistance, just like capacitance, is a purely geometric factor. It's the resistance of a thing with resistivity, rho, and then length, L, and the current is going through this area. And so that's just the resistance of it. How we understand how much current we get for a certain potential difference across the two ends is Ohm's law, right? V equals IR, where V is really delta V. It's the potential drop across the resistor, right? Go with the current. It's a drop. It's like going downhill with the water. Resistance in parallel. Awesome. And then, P equals IV. This is the power dissipated in any component. If it's a resistor that obeys Ohm's law, then you can get I squared R or V squared over R. And again, if they want to ask about power, you're looking for which is the most useful version of this, depending on what you know. And then, hey, guess what, guys? Look at all that magnetism. Goodbye. All right. See ya.